Okay, hi everyone. So I'm Bo. This is joint work with these authors, including Raf, who you just heard from, about property elicitation with multiple observations. So let me go back over property elicitation. So what's a property? It's just a function or statistic of a distribution that we'd care about. So like the mean, mode, are examples. What's property elicitation? Okay, well, so it basically asks the question, if I have this loss function and I'm trying to minimize expected loss, what am I going to get out? So more precisely, if I have observations drawn from some distribution P, and I'm trying to pick parameters R to minimize expected loss, what does this R star tell me about P? Like, what property of P is it giving me? And maybe I don't care exactly about R star, but maybe I can compute what I care about from R star with a link, right? And the terminology actually comes from game theory, where an expert who's strategic is reporting R, and they want to minimize their expected loss, and so we're eliciting this information from them. Okay, in learning theory, the motivation often comes from trying to understand statistically consistent losses. So just as one example, let's say that you care about 0-1 loss, but in your setting it's hard to compute, to minimize. You might like to know what are the set of, or the space of all losses that also elicit the same property as 0-1 loss, because then maybe you can use one of those as a surrogate. So it's nice to understand that space and be able to know the characteristics of different losses that do that. Okay, so to make sure we're on the same page, Raf kind of went over how if this loss function is r minus y squared, then you get the expectation of P, right, as your property. A basic negative result in elicitation is the variance. So you cannot have a loss function with a single parameter or a single dimensional R, such that this process gives you the variance, as long as this is a continuous link function. So you actually need multiple parameters. You need R to be at least 2 dimensions. So for example, you can have R be the mean and second moment, and your link function can compute the variance for you. Okay, and in general, you can always have R to be the complete distribution. So in this talk, I'm just thinking of discrete distributions on finite spaces, because math is difficult. But that's still, the number of parameters is the support size of the distribution, which is just way too many parameters, right? We want to minimize losses using as few parameters to set as possible. And so what you'd like to do in elicitation is study, for a given property that I care about, how many parameters do I need? So what is the dimension of R? What's the loss function that has the fewest possible parameters that can still elicit this property for me? Okay, so that's a general elicitation setup. In this work, we ask throw out a sort of oddball question, which is, what would happen if we modify the loss function to actually allow it to take multiple observations and use these multiple observations? And we were just curious what would happen if we tried this. And we had a couple examples in mind that seemed interesting or piqued our interest. So the variance, if you get 2 observations, IID, Y1 and Y2, now you can directly elicit the variance. You don't even need a link function with a single parameter R. Intuitively, that's because this expression is an unbiased estimator for the variance, and then I can use squared loss to elicit its expectation. A more dramatic example is the 2 norm. So we can actually prove that if you care about the 2 norm of a distribution, if you only get 1 observation, you're using this paradigm with a single observation, you actually need unbounded dimension or unbounded number of parameters. You basically need to elicit the entire distribution and use a link function to compute the 2 norm, which is no fun. But if you get 2 observations, that dimensionality drops all the way down to just 1. You just need 1 parameter. So we thought that was pretty cool. In terms of applications or motivation that you might care about, I would characterize this paper as being so theoretical that it verges on the hypothetical. But we do have in mind a few possibilities for when you might expect to get these multiple observations. So crowdsourcing could be an example, or numerical simulations. And I'll try to talk a little about regression at the end. Am I too far away? No? Okay. Okay, so I want to give you just a little bit of a flavor of the sort of math that we think about when we try to prove things in elicitation and how it changes in this paper. So we think a lot about the simplex of distributions. So this is a simplex on 3 outcomes. And what we call level sets, which are just the sets of distributions that have the same property value. So for the mode, I've shown the 3 level sets for this simplex. And you notice that they form a Voronoi diagram, and it doesn't matter what the definition is, but it's a nice geometric structure. And in general, you can show that for any sort of categorical property like this, you get a power diagram, which is a slight generalization. So we understand that pretty well. For continuous properties, you get these level sets which look like intersections of hyperplanes with the simplex. So they're very nice and linear. So this is all the distributions with mean 2, for example, and I'm showing a few of the other level sets. So everything's nice and linear and kind of clean in this traditional setting. Not quite so anymore. So here I'm showing a 3-category property that's elicitable with 2 observations. And it's very far from being like a power diagram or anything. And these sets, for example, the green set is not only not convex, it's not even connected, so things look very different. And what this property is saying is, tell me, are you close to uniform? Are you intermediate or far from uniform? Okay, and we can actually elicit this using the 2 norm with 2 observations. And the reason why turns out to have to do with the fact that these boundaries look like the zeros of a degree 2 polynomial, and the fact that we have 2 observations. And I'm not really going to tell you why, what that connection is, but I'm hoping to pique your interest with that fact. And I'm trying to show here this sort of intersection of the boundary with the simplex. And the same story holds here, and this is an example for the variance, which is very similar. Okay, and that's all I'm going to say about sort of geometric intuition or ideas that we're developing. So now I'll just say a bit about more concrete results. So we just try to give a few upper and lower bounds and sort of ideas for how to prove them. And what I mean by upper and lower bounds is, let's say if I just want to use 1 dimension or 1 parameter, how many observations do I need in my loss function to elicit the property I care about? Okay, so a cool example is the k-norm, or at least one that we could prove things about. So if you draw k IID samples, observations, the indicator for them all being equal is an unbiased estimator for the k-norm to the k of the distribution. And so you can construct a loss using that idea very easily that elicits it, and use a link to get the k-norm itself. Okay, you can have a similar approach for other things that look like this. The lower bound's a little bit more work, but the idea is that the k-norm of a distribution we can show requires k observations and cannot be elicited with k minus 1, the idea being that its level sets cannot be the zeros of any degree k minus 1 polynomial. Okay, and that's all I want to say about those results. And then I just want to give some intuition for why this might possibly be interesting to the rest of machine learning. Okay, so just throwing this out there, imagine you wanted to regress x versus the variance of the conditional distribution. Okay, so the problem is that previously you'd need to regress on the mean and second moment. And sorry, I'm going to have to wrap up fast. But if the mean and second moment follow very complex functions of x, then this regression could be really bad. And so the thing that you're computing for the variance could be really, really bad. But if you could somehow regress directly on the variance, then you could fit this simple relation of the variance versus x. But to do that, we know you need multiple observation loss functions. You can't regress directly on the variance in the traditional single observation paradigm. Okay, so that's it, and thanks very much.
All right, so we'll take a quick question while the next speaker is setting up. So I'll ask a question, actually. So in this setup where you look at expectation, you actually don't care at all about the variances of those unbiased estimators that you're actually building, right?
Yeah. So we're tending to think like very asymptotically. I don't know if this is answering your question, but so if you have a finite number of samples and you're doing ERM we don't know much about what's going on there yet.
All right. So let's thank Bo again.